Hello everyone, my name is Octavio Echeverria. I'm a member at Hyperlink and I'm the current head of electronics and software. Today, we want to briefly showcase our work, everything we've done so far and everything we want to achieve this year at Hyperlink in electronics and communications. Firstly, we will give you a quick tour of the whole system architecture. Then we will show the progress we made so far on electronics and software. And lastly, we will tell you our goals for next year. So this is a very high-level diagram of each part of our subsystem. Of course, this is not a complete picture as each block, as there's a lot of complexity hidden inside of each block. The dotted boxes represent the part of the system. It should be the location of the system, sorry. For example, this green dotted box should be the internals of the pod. This pink box should be the outside or everything we need to access from outside of the pod. And this blue or sky blue color represents our remote control station. This big orange box represents our communication protocol we've chosen to control most of the electronics on the pod. We chose CAN bus, as it is a very common and very flexible and powerful communication protocol, and is widely used in various types of industry. And all components we've purchased so far or we plan to purchase or we are designing are compatible with CAN bus. Everything that's orange on this diagram represents communications. The green boxes represent everything we have acquired or we are planning on acquiring. For instance, this green box on the left that says computer is a Linux-based computer. This will handle all our communications and also will allow us to use more complex control schemes. While it's entirely possible to upload all the computation to a remote computer on our ground control, it's very hard to justify all the loss in robustness since these small computers are often very small and cheap and efficient. The remote computer on the left will serve mostly as a remote control. We will be able to control most of the functionality, if not all the functionality of the pod, while also we will be able to monitor. We will be able to monitor the most sensor readings. My computer is getting hot. And also control also works as a safety switch. So we should be able to disengage the pod while from the remote computer. This green box in the middle between the computer and the CAN bus is our CAN bus transceiver, since most computers don't come with a CAN bus interface to communicate with the other modules. Our power design requires 2 voltage system, which is very common, high voltage and a low voltage. Both are batteries. So the high voltage system comes with a BMS as well as the low voltage system, which is a battery management system. This is mostly for safety. And this BMS will transmit back all the sensor readings from the battery packs. For example, the cell voltages, the currents, and the temperature of the cells. The blue boxes represent everything that we've built from scratch or we're building from scratch. For example, the braking electronics. This module will be responsible for reading all the pneumatic pressure from our pneumatic system. as well as controlling the valve that interacts with the brakes. And the sensor board will interface with all types of sensors, since sensors come in various types, and for example, analog sensors or digital sensors, as well as many other interfaces such as IO-Link, serial, or Modbus. This board will simply connect them all to CAN bus, and so that all these sensors can be read from the computer. And the different outlines, for example, this yellow outline here represents which voltage or which power system is it connected. For example, the charging port and the chargers are connected to mains. The purple outline represents high voltage, so it's mostly just the BMS, the battery pack, and the inverters, as well as the pink outline, which represents low voltage. So it's mostly for powering the computer, the electronics, and the low voltage battery. So our system uses 2 inverters because we are using 2 motors. These inverters are the only device connected, or the only thing that requires high voltage. And these as well are selected because these are compatible with CAN bus. So everything is controllable with CAN bus, and that makes wiring a lot more easier. And since CAN bus has a lot of error management, it is also a lot safer. So in the outside control panel, we will have a display for monitoring values and doing last-minute checks. We also have e-stops and switches for disengaging batteries and different subsystems. We will also have indicator lights. So this is the hardware from last year. This is a very highly modular system. Each subsystem has its own board, which makes it very redundant and safe. And there was a board for propulsion. There's also a board for braking and a board for power management. These are all connected using CAN bus, which reduces wiring considerably. And these microcontrollers are based on the STM32 ecosystem. We use for most of this board only 2 types of microcontrollers: the STM32 F103, which is labeled as a general use microcontroller, and the F405, which is a high-end microcontroller. The firmware was RTOS based, which means real-time operating system. This will allow us for a lot more control of the readings and actuators, of the sensor readings and actuators. And the main board also has an IO-Link interface for using more advanced or more high-end sensors that requires this type of interface. We have for that and photoelectric sensor. So this is the motherboard from last year. This uses the 405 microcontroller, which is a ARM core M4 architecture and 168 megahertz, so it's very fast. This implements a lot of interfaces. It can implement CAN bus, IO-Link, Ethernet, USB serial. So most of the stuff can be connected through here. And it was mainly used as a communications hub and as the main controller. So last year, the whole control loop ran from this board. We also have the teleboard. which was based on the STM32F103, which is the more middle of the road microcontroller. So it has a CAN bus connectivity, so it connects to the whole system with a single cable. It has 6 channels for 24 volts DC output. So that's mostly for operating the valves on the braking system. And 4 channels for pressure sensing, and 3 channels for temperature sensors, and an encoder for reading the speed of this suspension wheel. Last year's software implemented a final state machine for decision making and for state transition. The telemetry was done via UDP and implemented a whole networking stack via Ethernet. So the main board had a Ethernet interface, a physical Ethernet interface, and the firmware itself was responsible for the networking stack. It also had the I/O link drivers for reading the sensors, and implemented CAN bus 2.0 at 500,000 bits per second. And they also implemented their own CAN-based communication protocol, a layer between 3 and 4, in a way parallel to CAN Open, which is a very common protocol. Here on the right, you can see the graphical interface from last year. So it can monitor the state of each board, the state of the system, they can modify the cruise time, braking distance, and also the connectivity can be done through it. So what's next for 2023? We plan to increase power substantially. We estimate a 100x to 1000x power increase, so that our project can be more competitive with other teams in the competition. Likewise, we increase computational power, and this is the reason why we included onboard computer. The computational power will allow us to use more complex algorithms and control schemes. We also want to increase the sensor count to make sure everything should be operating at a safe level. We want more temperature sensors everywhere, particularly on the motor and the brake pads. We also want to increase safety. We want to have a redundancy in sensors, redundancy in switches and brakes. We also want to support eddy braking and regenerative braking. This is to ease the load on the braking system, so that way we can guarantee even more braking power and increase safety, as well as a better heat management. Now considering that the pod itself should operate on the vacuum. For the software, I talked about higher level control strategies. This can be done multiple ways, and a lot is being unlocked by using a computer instead of a microcontroller. For example, you can run different programming languages. If we want to implement a control system on MATLAB, we can now do that. Also, we can do Python and Simulink or whatever other way to program is already achievable by using a computer. Also, graphical interface should be very easy using a computer. If we were to use a microcontroller for it, it would be very hard and time-consuming. We also want to increase data collection for analysis to make sure we can improve our modeling or our knowledge of our own system. And these last few are a bit of of a wildcard, we want to use ROS-based communication. If you're unaware, ROS is a framework used mainly for robotics and robotics research mainly, but it's lately been used for a lot of commercial robotics, and various companies are using it for autonomous vehicles. Now, this will mean that we are treating the part more like a robot and less like an electric vehicle. But ROS will allow us a lot of safety, since it's an open source project, and it's very a lot of development is done to it, and it simplifies a lot of communications. Also, it will allow us to implement commercial high-level controllers and more complex or just plain better systems, because ROS separates each parts in nodes, and these nodes can be plug and play. So you can easily implement an LQR controller without needing to manually implement a LQR, say in Python. And also we want to move away from finite state machines. They are very hard to maintain and very hard also to extend. And this is also compatible with ROS, because ROS has a library for behavior trees, and our behavior trees should be more easily manageable and easily to implement than a finite state machine.